In a random sample of size 1,000, so what is the probability that fewer than 500 women are selected? Use the binomial model and the normal approximation and compare the results. Okay, so binomial. We're just going to do kind of a shortcut here. Binomial, you know the process you have to go through, right? So we're just going to use our calculator to find the binomial. So in the binomial model, what is n in the problem? N is 1,000? Okay. And x is, well, it's probability that x is less than what? 5, or just less than 500, okay? P, the probability of success is what? 0.51. So what's Q? 0.49. So in my calculator, what can I type for the binomial? It's just less than. For 499. So I'm going to do binomial CDF. N is 1,000. P is 0.51. And why do I have to go 499? You're not including 500. It's just less than 500. It says fewer than 500. So I'm not including 500, so I have to do 499. And so the binomial second distribution, binomial CDF, 1,000 people are being asked, 0.51 and 499. And what do you get? 0.2532? 33? No, I just got 2.
Yeah, I guess.
3.2 because the next digit's 4 is what I got.
Oh, well, I go after 4 is 9. So
No, that's kind of weird rounding, but
Yeah.
no, you just look at the one directly next to it. Okay, so that's the binomial. So now let's change it to normal. Okay, so can I change it to normal first of all?
Yes.
Can I change to normal? No. Well, I don't know. What do I have to check? What does it say on the bottom of the previous page you have to check? N times P is greater than or equal to 10 is greater than 10, and N times Q is greater than 10. Greater than or equal to. That's what I have to check before I can change it to normal. I don't just change it to normal, I have to see if it's okay to. So my N in both cases is what? 1,000 times 0.51 and 1,000 times 0.49. Isn't that 510 and 490? Aren't they both greater than 10? So is it okay to change this binomial to a normal model? Yes. Can I change to normal? Yes. Gotta check that. Okay, so now if I change it to a normal model, x was binomial of 1,000, 0.51. So now what do I calculate to change it to normal? Mu is N times P. We already found that is 510. And sigma is the square root of N times P times Q. So second square root, 1,000 times 0.51 times 0.49. So what's sigma? Round it to the nearest whole number. 16. So x is now approximately normal with a mean of 510 and a standard deviation of 16. Now I'm actually going to draw the picture here. Okay, draw the picture. So 510 is the mean. If I add 16, I get 526. Add 16 again, 526, 536, 42? I don't know. I'll probably mess it up. And then 558. And then I subtract 16, so 510 minus 16 is 494, minus 16 again. And the reason I'm drawing it, that helps me decide my upper and lower bounds, and I draw a picture of it. I know I'm going to get credit on the AP test. So here's my normal distribution, and I want to know the probability that x is less than 500, so isn't 500 about right in there? There's 500, and less than that is right down here. So now I'm going to do NCDF. What's my lower bound? No, it's not. Look at the picture. Now, in a normal model, this is negative infinity over here, and this is positive infinity up here. So in this picture, look at where I shaded. What is on the left? Lower bound is what's on the left of the picture that you shaded. Negative infinity. So since my upper bound is then 500, how many 9s do I at least need to type? 4. 4, 4, 4, 9, 4 9s, and then 5,000 or 500. And then what are the other commands? Mu and sigma. So mu would be 510 and sigma is 16. So second distribution, go to NCDF, bunch of 9s, upper is 500, mean is 510, standard deviation is 16. And what do you get for your probability? 0.266, that one does change to 60. Is that very close to what we got when we used the binomial? Is 0.25 pretty close to 0.26? Yes, they're very close to each other. So is it pretty good approximation? Is it exactly the same? No, and it won't be, okay? And
So, yeah.
which is more accurate? If it's a binomial distribution, the binomial is more accurate, okay? If it's a binomial distribution, the binomial is more accurate.
So normally it wouldn't ask you to find the binomial.
Normally it wouldn't, but the reason we're doing it is so
Yeah,
that
to
you could
compare.
see
Yeah, okay.
that it is a good approximation. Now, that's only if this quality holds here.
Yeah.
If this didn't hold, if they were less than 10, then these would be way off. These would be very different from each other. And if it's a binomial, the binomial is always a better approximation. Now, what happens when n is really big, though, when you do a big number of trials, the binomial and the normal become about the same. So, all right, we're just about done. In a sample of size 10, now here's an example of when it doesn't work. Okay, so we're going to do the same thing we just did, but this time n times p and n times q are not going to be greater than 10. Okay, so in a sample of size 10, what is the probability that fewer than 5 women are selected? Use the binomial and the normal and compare the results. Okay, so this time the binomial, okay, what's n? 10. What's p? 0.51. And we want to find the probability that x is less than 5. So x is binomial 10 comma 0.51. Okay. So now we're going to do binomial CDF. And we're going to do 10 comma 0.51 comma what? 4. Because it's less than or equal to. So we have to do, in this command, we have to do 4 instead of 5 because we just want fewer than 5. Okay, so that's going to give us second distribution. Again, we're just doing a comparison here. 10.51. The first time we did this, we asked 1,000 people. And the normal model, we asked the same. And our x value is 4. And now we're only asking 10 people. So we want to compare the results of using binomial versus normal. So this time, what do you get for your binomial probability? 0.35. 3526. Okay. So now, if you just check n times p and n times q, n times p is 5.1, n times q is 4.9. Are they greater than 10? Okay, so these are not greater than or equal to 10. So basically, that should be a red flag right there. That if you're going to change this to a normal, it's probably not going to be that good of an estimate. So now I'm just going to show you that. So if I change this, if you change this to a normal model, you'll get the mean is n times p, which is 5.1. We already found that. If you check the condition, you have already found the mean. And then the standard deviation, the square root of n times p times q. You notice I don't plug the numbers in. I just write the formula down and plug the numbers in my calculator. I mean, writing the formulas down is what the AP test really wants to see. They want to see the formulas and then the answer right after it. If you want to plug the numbers in, that's fine, but you don't have to. So 10 times 0.51 times 0.49, which is the standard deviation would be 1.58. So now if I change it to normal, x would be approximately normal with a mean of 5.1 and a standard deviation of 1.6. We'll just round to the nearest tenth. So this time, 5.1, 6.7, 5.1, and that's going to be 3 point something. Okay, so here, if I'm using this normal model, less than 5 would be like right here. So what would be the lower bound on this NCDF? NCDF, the lower bound would be negative 99999, 4 nines, and the upper bound would be 5, and the mean would be 5.1, and the standard deviation 1.6. So second distribution, NCDF, negative, I already have negative infinity in mine, and then 5.1, and 1.6. And this time I get 0.4751, which actually makes sense based on my picture, because it is, still in that first, close to the mean. Are these two close at all? No, these are not close, not close. Over on the other side they were. Here they're not. Why not? Because the condition, the important condition, n times p and n times q, was not met. So even though our calculator can handle any reasonable sample size, we need to use the normal model approximation to the binomial when we do inference procedures for proportion in future chapters. Basically, later on we're going to change everything to normal, is what this is saying. Okay, everything's going to eventually go to the normal distribution when we do what's called inference procedures, or making decisions based on statistics. So, all right, so your homework, you've got, 4 whole pages to read. And 5 homework problems. So they're all odds, but I expect questions probably. And then next time we get together, we are going to just do some review. It'll probably take me a while to go over questions on this. We'll do an AP question and you'll work on homework. So we'll just be practicing some of these 2 things before we move into chapter 18, which is called sampling distributions. So, all right.